All information collected by Earth-observing satellites is derived from the waves of the electromagnetic spectrum. All the more reason to take a closer look at the electromagnetic waves and their properties. As the name reveals, electromagnetic waves consist of two components: a constantly changing electric field and an equally changing magnetic field. Both travel in the same direction and are perpendicular to each other. Electromagnetic waves can be described by their wavelength, their frequency, and their energy content. Let's look at wavelength first. Points on this wave are similar in their position. You can see it quite clearly on the wave crests and troughs. As the wave moves up and down, these points stay in the same position. They can also be described as having the same phase. The distance between the points in the same phase is the wavelength. It is measured in units of length and can range anywhere from kilometers to picometers. The frequency, in turn, shows how fast a periodic process repeats. In the case of waves, this means how often does the same phase repeat itself per time unit. The unit hertz describes this ratio as phase repetitions per second. Electromagnetic waves do not require a medium such as air or water to spread. Gases or liquids even slow them down. Only in a vacuum can they travel without obstacle, at a speed of almost 300,000 kilometers per second, which is the speed of light. Each wave, regardless of its length, moves at the speed of light in a vacuum. For the waves to travel at the same speed in the vacuum, the speed of light, the frequency must increase for smaller wavelengths. The frequency increases due to the shorter waves needing to cover the same distance as the longer waves. Since the phases are closer to each other in lower wavelengths, this results in an increase in frequency. Wavelength and frequency also decide on another property of the electromagnetic radiation. With higher frequency and shorter wavelength, the energy content of an electromagnetic wave increases. The common phenomenon of sunburn proves this principle perfectly. Sunburns are the result of cell damage in our skin due to high-energy, shortwave UV radiation. What causes this energy increase? Well, to answer this question, we must dive into the complex world of quantum mechanics. Let's try to keep it as simple as possible, though. Quanta are the smallest building blocks of the universe. Light is also made up of such quanta, which we call photons. As we know, light spreads in ripples. This has been proven experimentally. However, photons behave like particles, and at one point in time can only be in one place, which contradicts our model of the continuous light wave. Whether light quanta are particles or waves is unanswerable. They are both. And depending on how you measure them, they are either one or the other. We present them here as both, and of course, that's incorrect. Welcome to the world of quantum mechanics. Fortunately for us, only one relationship is important at this point. The higher the frequency of the wave, the greater the energy the photons carry. A red light photon thus carries less energy than a blue one. So, as the frequency increases, so does the energy content of the wave. Wavelength, frequency, and energy. Each one of these electromagnetic properties decide on which part of the electromagnetic spectrum becomes useful to us when we are measuring our environment. For example, only the high-energy shortwave X-ray radiation can penetrate through our body. Heat is radiated in the wavelength ranges of the thermal infrared, and our eyes rely on the wavelengths of the visible light to perceive colors. If satellites are able to provide us with a recognizable image of our Earth or measure the temperature of Earth's surface, then their sensors must record the parts of the electromagnetic spectrum that carries this information.